Okay, for this question, we'll see where is this piecewise function discontinuous, and we'll also categorize it, what kind of discontinuity it is. Well, for this, of course, the suspect is when x is equal to 0, right? Because it's a piecewise function, and that's the endpoint. And you can do this two ways. The first way is make your graph first, and the second way is do limits first. Up to you. I will do the second way. So here we go. We are going to check the limits. So first of all, I will check the limit as x approaching 0 minus of the function. And when we do this, of course, we are looking at 0 minus. That means a little bit less than 0. So we are looking at the first piece. And we can just go ahead and calculate the limit as x approaching 0 minus of cosine x. And for this, we can simply plug in 0 into here because, in fact, it will give us a very nice value, which is 1. So that's it for the limit for that. And we'll go ahead and check the other direction when x is approaching 0 from the right-hand side of the function. And we know this is the limit as x approaching 0 plus. Well, for this case, we're looking at the third piece, which is 1 minus x squared. So go ahead, plug in 0 into here. And again, you don't have to worry about the 0 plus or whatsoever, because when we do this, we get a nice value. 1 minus 0 squared, of course, that will give us 1, right? So this is very good. However, notice that although they are the same, and yes, this right here together will tell us that the limit when x approaching 0 without any plus or minus, and of course we have the function f of x, and this right here is just of course equal to 1 because they are equal. So yes, we do have a limit when x approaching 0. However, this does not tell us the function is continuous when x is at 0, because we also have to check the value of the function when x is exactly equal to 0. So notice that when we have f of 0, when x is exactly equal to 0, by definition, we get 0. Ooh, the problem is that the limit is not the same as the value of the function. So it's still not continuous. And in fact, in this situation, we actually have a removable discontinuity. So I will just write this down here for you guys. First, f has a removable discontinuity at x equal to 0, and the reason is because, right, based on our computation, and we see that because the limit as x approaching 0 of the function, this right here is not equal to f of 0. So remember, this is pretty much the main check to see if a function is continuous at that x value or not. If the limit is not the same as the value of the function, no good, right? And sometimes the limit doesn't exist. In that case, you may have a jump or you may have a vertical asymptote. So again, in that case, no good. But in this situation, the limit exists. However, it's not the same as the value of the function. We actually have a removable discontinuity, right? Okay, so now let me take some time to make the graph for you guys, because once we see the picture, we see everything. Okay, when x is less than 0, we graph cosine x. And we know cosine 0 is equal to 1, but we do not have a closed circle when we are at x equal to 0. So, because it's just less than, right? So I will just come here and open a circle here, and I will have to graph the cosine wave, but I will go backwards because it's a x less than 0 situation. So it's going to look something like that, right? So this part is the cosine x. And then when x is at 0, we graph 0. So that means we have a point right here, right? And lastly, when x is bigger than 0 but not equal to 0, we graph 1 minus x squared, meaning a upside down parabola, and you shift it up 1 unit, and again just the right hand side. So 1 minus x squared is just going to look like this, right? So again, this is the 1 minus x squared, and this is the cosine x. With this picture you see, this right here is a removable discontinuity when x is at 0. So that's it. Remember the computational part? I think sometimes it's becoming handy, right?